Hey everyone, so this is problem 2.7 out of Griffiths' Introduction to Electrodynamics. We're going to go through this problem together, but before we get into that, I just want to ask if you wouldn't mind liking this video and subscribing to my YouTube channel. I'd really appreciate it. I post a lot of videos that work through different sorts of problems from popular undergrad textbooks, so I think a lot of you would benefit from it. Plus, it's a free way to support me. Okay, so let's get into this. We have an electric field produced by a particular charge distribution, and we want to find the electric field a distance z from the center of a spherical surface of radius r that carries uniform charge density sigma. And it gives us a hint to use the law of cosines here. So let's just talk a little bit about what we'll need. To begin with, we have this equation for our electric field given some charge distribution. This is our main equation that we will always use with these sort of questions, so it's important to know. Also, very useful in a lot of EM problems, and in this one, as noted by the hint, is the law of cosines, which, if you have a triangle with legs ABC and an angle gamma opposite of C, you can express C squared as the sum of the other two legs squared minus 2 times the length of the two legs times cosine of that angle. And then this is just the diagram. So you can imagine this kind of looking at some sort of sphere here. This is the center, and this is supposed to at least be a vertical line going up to some point P. And then this is just some arbitrary charge distribution. It could have been anywhere. I just picked here. And it's a distance script r from the point in interest. And if you remember in spherical coordinates, this angle from our r vector from our vertical is what we call theta, and it's obviously going to be a distance r from the center since it's a sphere. So this little surface is what we're considering, and that's what we're going to work with, and we're going to integrate over that. So let's go ahead and start breaking this down. First off, that little bit of charge is sigma dA. So that's your charge distribution times that little chunk of the surface area, dA. So our dA in this case is r squared sine theta d theta d phi. So I think this was derived in chapter 1 material, if you're not sure about that for the dA of a sphere, but that's what that is. Next up, script r. So once again, script r is going to be, since angle theta is opposite of that, script r is going to be the sum of the square of the two legs of the triangle minus 2 rz cosine theta. Okay, so if we look back at our equation, we have our charge distribution. We have r squared. Now, the other thing we want to do is, if we look at this and you think about the electric field, this has been a reoccurring theme with these sort of problems. Whichever charge distribution you pick, as you go around the circle, these horizontal components will cancel. So the horizontal components given from the dA in white might cancel with this particular dA prime, we can call it. At least the horizontal part of it will. Of course, there's still the vertical part, that's to say the part in the z direction. So this was basically the same argument as previous problems, where you can use the symmetry of your geometry to simplify the problem. So we really only want this part. So how are we going to do that? Well, we can do something pretty similar, and we can say that r squared, so we'll call this angle gamma, r squared is equal to z squared plus script squared minus 2zr cosine gamma. Okay? And what we want to find is this cosine term, because this cosine term will just be the part that we're looking for. Okay. So we can do that 2zr cosine gamma. So I move that over to the left. I'm going to move the r squared over to the right. But this script r, we can substitute that in. So that's z squared plus r squared plus z squared minus 2rz cosine of our angle theta. And then we have our minus r squared. Now we want to solve for cosine gamma, so we'll also divide by 2 times z times r. Clearly these r squareds drop. These two z squareds will turn into a 2z squared, right? But these 2's will all cancel. And what else will cancel? Well, one of the powers of z. So you can see the cosine gamma term actually cleans up pretty nicely. And what are we left with? Well, we have a power of just z now in the numerator minus r cosine theta divided by so this actually needs to be not that r, it needs to be script r, because that's what our law of cosines is. So that is my fault. So that should have been a script r, and this should have been a script r. Okay, so this divided by script r. So essentially what we're going to do to take care of the direction of this, we're not really going to worry about the hard hat. We're going to put in a cosine of gamma, which we just solved for. So then what is our electric field? Our electric field, we have our constants out front, of course, 1 over 4 pi epsilon naught. We're integrating over an area, so it's a double integral from 0 to pi, 0 to 2 pi. So we have our dq, which is sigma r squared sine theta. There's the differentials, but we'll put that at the end. Sigma r squared sine theta. Okay. Then we have, we're not doing our r hat, we're multiplying by cosine. So times z minus r cosine theta, all divided by, so there's a script r from here, but there's also an r squared here, right? So we have an r cubed term, and then we have d theta d phi. Now what is r cubed? Well, probably should have done this earlier, but we know what r squared is, or script r. So then this is just the square root. Cosine theta. Okay, or if it's helpful, this to the 1/2. Because if we want the third power, then this is just going to be to the 3/2, like that. So with that in mind, I'm going to come down here, and instead of putting that, I'm going to put r squared plus z squared minus 2rz cosine theta all to the power 3/2. Okay. So I'm going to try to simplify this integral a little bit. To actually work through this integral is a bit much, and I'd really recommend either getting some sort of integral table or honestly just using an online integral calculator. I think most of you are okay with this. At a certain point, you only have so many hours in the day, and you really want to not spend a lot of those hours doing calculus that you could do, you have done, but this isn't a calculus class. This isn't testing how well you are at solving integrals per se, unless it's something you can do decently quickly. So instead, I'm going to emphasize how to put this in a form where solving it or putting it in an integral calculator will be easy. So first off, none of these terms in the integrand have a phi part. So your d phi will just turn into a 2 pi. So we have 1 over 4 pi epsilon naught. Sigma and r squared are both constants, so that can come out. And then, like I said, when we integrate d phi from 0 to 2 pi, it's just 2 pi. And now this double integral is just a single integral. It's already a little better. Sine theta times z minus r cosine theta all divided by r squared plus z squared minus 2rz cosine theta to the 3/2 d theta. At this point, I would just plug this into an integral calculator. If I had to solve this, I would distribute this sine theta term, break it up as two integrals. My guess is because of this 3/2 in the bottom, you might get stuck with some sort of trig integral. Maybe you could do some sort of u substitution to make it a little nicer, but it's just unnecessary. I will say what you should get is something at least equivalent to 1 over 4 pi epsilon naught 2 pi r squared sigma over z squared z minus r over the absolute value of z minus r plus z plus r divided by the absolute value z plus r. Now, there is technically one other part. So this was all for z greater than r. That's what we assumed. If z is less than r, it's actually really simple because there's no charge distribution that you're going to see inside. So the E field is just 0. Okay. So that's how you solve this problem. Hopefully it was helpful. And if it was, please like and subscribe. Thank you.